This is Daniel Coosbury, and in this lecture, we're continuing to look at geometrical properties and whatnot, and we're focusing on volume and surface area. So now we're dealing with three-dimensional objects. And so when you have three-dimensional objects, we can talk about volume, which is the space the object takes up, and we can also talk about the surface area, which is the area of all of the sides of that particular figure. And so we're going to do both. Most of this is going to be volumes, and I'm going to throw a lot of formulas at you, and then we'll look at surface area, and there's a few formulas associated with that as well. But for volume, we'll start with box-like shapes, and we have rectangular prisms, we have cubes, and the volume formula is rather straightforward. It's length times width times height. So if you have three dimensions, there's a dimension of length, a dimension of width, and a dimension of height. You have those three things with a box-like shape, and then you have your volume. With a cube, it's simpler because a perfect cube has all the length, the width, and the height. They're all the same thing, so we can call that s cubed. But they're essentially the same formula. So if we wanted to find the volume of this rectangular prism here, we would do length times width times height, 3 times 3 times 4, and we would get 36. And then we're going to cube our units when we deal with volume. So like when we squared the units with area, because we're in 2 dimensions, we're going to cube our units with volume. So we're talking about cubic inches. This prism takes up 36 cubic inches. Okay, so let's look at an application problem. We want to make a walkway that is 15 feet long and 8 feet wide and 9 inches deep, which means it's going to look kind of something like this. It's going to be 15 feet long. And my drawing probably not that great. And it's going to be 8 feet wide, and then it's going to be deep because we're pouring concrete into the ground, so it's going to kind of look like this. And it's going to be 9 feet deep. And other than that, like we're going to assume it's some sort of a rectangular prism because we're not told that it's curved or whatnot. We're given these 3 dimensions, so we'll use these 3 dimensions. Now, the problem asks for the cost of the concrete in cubic yards, which we're not given anything in yards. So I like to do these conversions before I actually get to the cubic thing because it gets a little tricky. I'm going to go ahead and convert 15 feet to divide that by 3, you get 5 yards. 9 feet, you divide by 3, you get 3 yards. And if you do 8 feet divided by 3, you end up with we'll just kind of round 2.7 yards, or 2 2/3 yards. And now I've got my length, my width, and my height in yards, so I can find the volume in yards. So it's 5 yards times 3 yards times 2.7 yards, which gives me 40.5 yards cubic yards. So then the problem asks for the cost, where the concrete costs $30 per cubic yards. So if I want to find the cost, I have my 40.5 cubic yards, and I'll do some kind of unit fraction here where I have $30, so $30 per cubic yard. So I made a little unit fraction here where the cubic yards cancel out. My dollars is my unit, so I have 40.5 times 30, and I get $1,215. That's the cost of my concrete. So again, I really like to convert the units before I actually do any multiplication because it's just a little more straightforward. But yeah, so that's how we would do that. Is we found the volume, then we would multiply it by the cost using kind of dimensional analysis that we've used before. Okay, here's a pyramid. So the volume formula for a pyramid is 1/3 base times height, where the base is actually going to represent the area of the base. So you have different kinds of pyramids. You have pyramids with a square base or a rectangular base, and you've got pyramids with a triangular base. Whatever that base is, you're going to take, or whatever the base is, you're going to find the area of the base and then multiply it by the height, and then multiply that by 1/3 to get it. So it's just not as straightforward as having a B. Sometimes you have to find out what that B is, find out what the area is. So here's an example. We're going to look at the Eiffel Tower, and even though it's not a solid pyramid, we're going to just kind of assume it's a pyramid so we can approximate the area. And it says it has a square base. with 120 feet on a side and a height of 980 feet. So what we're dealing with then is we've got some kind of a square base, and then, I'm not very good at drawing pyramids, then you got a height of 980. So that means that this side is 120, this side is 120, and the other two are 120. And then let me also mention, just kind of like when we did area of triangles and parallelograms, for the height to truly be the height, it has to be perpendicular with the base, and it's got to go to the tallest point on the pyramid, which is that middle point right there. So the height here, it's perpendicular. That height, it's getting a little messy, is 980. Okay, so I'm going to find the area of the base first, just so that I can use my formula cleanly. The area of the base is going to be, it's a square, so it's going to be the side squared, 120 squared, which is 14,440. Nope, 14,400. That's going to be in square feet. So then my volume of the pyramid is going to be 1/3 times the base times the height. So you see what I did? I had to calculate the base first before I could actually use this formula well. And then I'm just doing multiplication now to get my volume. And when I do that multiplication, I get the volume is this. And that's approximately the volume of the Eiffel Tower. Now it's not perfect because the Eiffel Tower doesn't look like, it's not truly a pyramid, but if it were, that would be the volume. And that's probably a little bit of an overestimate, but in case you wanted to know. Okay, we got more formulas. We can look at a right circular cylinder. Now a cylinder has a circle for the base and it's a certain height. What makes it a right circular cylinder is that there's a right angle that can be made. If you connect the top and the bottom, it makes right angles. So that's a right angle. That's a right angle down there too. And so with a cylinder, we have pieces. We have the height of the cylinder and we have the radius of the base. And with those two things, we can find the volume. So let's go ahead and look at this one. Here's a cylinder turned on its side, just to kind of get us used to how this formula works. The height of the cylinder is going to be from base to base. So this 12 is going to be the height. And then, so I'll go ahead and kind of write that out. The height is 12, even though it's turned sideways. And then the radius is going to be the radius of the base. Now we're given this length, which goes across the base and it goes through the center of the base. So we'll call that the diameter because it goes all the way across and it goes through the center, which means the radius is going to be half the diameter, which is 7 centimeters. So then the volume is going to be pi times 7 squared times 12, which we could write as, if we wanted to be precise, we could write it as 588 pi centimeters cubed, or we could approximate it by doing 588 times pi and getting 1,847, and I'll round to maybe 2 decimal places. And that's the approximate volume. So you can write it perfectly with without rounding pi to 3.14 or something like that, or you could find the approximate thing by converting it to a number. So that's that. And then we have a cone. The cone works very similar to a cylinder. The cone has a circular base and a top, and the volume, for the volume, all you need is the radius and you need the height. So the height is the perpendicular distance from the base to the top, kind of like in a pyramid. And then the radius is going to be the radius of the base here. So here's another cone in which we're given the height. See how it's perpendicular with the base and it goes all the way to here. It's just flipped upside down. The height is going to be 7 yards. And then what is also given is the width across, the length across this base here, which is, we'll consider our diameter. So we want the radius, it's going to be half of that, 3 yards. And then we can use the volume formula. So the volume of this cone is 1/3 times pi times r squared times height. Which, if I wanted to, I could write this as 21 pi, and then this will be in cubic yards. Or I could approximate that by multiplying 21 times pi and I'll get 65.97 cubic yards. Notice I'm using my little squiggly equal sign. It's approximately that. It's exactly this number where pi is 3.14 and a bunch of other stuff. So you notice a lot of these volume formulas are really similar, and I guess what you need to use them is to be able to identify the appropriate pieces, namely the radius here and the height here. Okay, and the volume of a sphere is given by this formula. A sphere is a three-dimensional point in which the radius, or the points on the sphere are all the exact same distance from the center, kind of like in the circle, all the points are the same distance from the center. The sphere is a three-dimensional version of that. So this radius, kind of any point on this sphere, this three-dimensional sphere, is the same distance from the center, so we'll call that the radius. And so all you need is the radius then to find the volume of the sphere. And instead of just doing one of these, I have a kind of a more complicated figure, we're going to use a couple formulas to find this. So find the volume of this. So what it looks like is I've got a cone down here, and you can kind of see the base of the cone in that little shaded line here. And then it looks like we have half of a sphere on top. It's not a whole sphere, but it looks like half of one. And so we're going to assume that's what we're looking at, is there's a cone and then half of a sphere. And so we're going to find the volume of each one. Let's call this half sphere figure 1, and let's call this sphere figure 2. So when I write some things, you'll kind of know what I'm doing. So let's start with the volume of figure 1, and we're going to use the sphere formula, which is 4/3 times pi times the radius cubed. Now I'm given what looks like the diameter again, so the radius is going to be half of that cubed. And then, so that's my volume formula. That's what this is right here, this whole thing. And then, since I'm given only half of a sphere, let's take that volume and multiply it by 1/2. So I'm doing a lot of things all at one time. I got the volume of a sphere with a radius 6, but I'm only want half the sphere, so I'm going to multiply all that times 1/2. And I'm going to go ahead and skip the whole having an answer with pi in it, and just go ahead and approximate for pi, just because it's going to get messy. So let me use my squiggly equal sign. So this is 452.39 centimeters cubed. So that's the volume of this half sphere up here. So again, I used the sphere formula, and then I multiplied it by 1/2. And then for the cone, I need the cone formula, which I've already forgotten, but there's a formula for it. It's back here. The cone formula is 1/3 times pi times r squared times height. So I'm going to do 1/3 times pi. And then my r squared, let's see, it looks like the radius of this cone is the same as the radius for this half sphere. So that's going to be 6. And then my height is going to be 15. So that's my cone formula. And that's a full cone. I don't have to multiply it by anything else. It's a whole cone. So this is going to be equal to, it's a lot of calculating to do, 565.49. So that's the volume of the cone. So then my volume of the figure is just going to be the sum of those two volumes. So I found the two pieces, and I can just add those things together and get my final answer. So it took using a few different formulas to do this, but we kind of broke the problem into two simpler problems, and then we just had to add our answers together to get the answer. And this is what I got for the volume of this figure, this half sphere plus this cone. So that's that. So once you get comfortable using these formulas, then you should be able to look at a few more complex shapes and adapt those formulas to your needs here. So that's what that's the last thing we're going to look at with volume. And the other part of this section is surface area, and I have 3 surface area formulas that are rather simple. So the surface area is just the sum of the area of all the sides of the figure. So here's how you find the surface area of a cube. It's just 6 squares. So S squared is the area of the square. 6 of those, 1, 2, 3, 4, 5, 6. Same with a rectangular solid has a similar idea. You're calculating the area of 6 rectangles, except there's going to be each side is going to have kind of an opposite side with the same area, so you can kind of calculate the area of 3 rectangles and double them. And then the circular cylinder is a little more complicated, and I'll just kind of point to that formula there. It's the area of these 2 bases, and then this is kind of a messy area of that. So we're just going to use one of them, and I'll trust you can identify the length, the width, and the radius and things like that to use these formulas. But here's a solid, and we want to find the surface area of the solid. So I'm just going to take this formula and just plug things in to it. So the surface area is going to be 2. Let me just call them things. So this is the length, this is the width, this is the height. Doesn't really matter what's what in a prism. So this is going to be 4 times 6, length times width. This is going to be length times height, so 4 times 3. And this is going to be width times height, which is 6 times 3. And honestly, I've just plugged everything into this formula, so whatever number this is should give me my surface area, and that's all the work I have to do. Of course, this is a simpler formula than the cylinder one, but they all kind of work similarly. You plug in the things correctly, you use these parentheses the way I use the parentheses, and you should get 108 meters cubed. So given any of these 3 figures, if you can identify the side length in a cube, or the width, length, height in a rectangular prism, or the radius and the height in a cylinder, then you should be able to find the surface area. It's just a little more complex formula. You're still just plugging things in. So that's really all we're going to talk about with surface area, is just use these formulas and you should be fine.